Green hydrogen is supposed to be the fuel that fixes everything. It promises to decarbonize steel, clean up shipping, stabilize renewable grids, and unlock entire new energy systems. Governments are pouring billions into it. Companies are announcing massive projects across Europe, the Middle East, Australia, and the United States. On paper, it looks unstoppable. But when you step away from the announcements and follow what is actually happening on the ground, a different story begins to emerge. Projects are delayed, costs are rising, timelines are slipping. And across the industry, one quiet reality is becoming harder to ignore. Green hydrogen is hitting a wall. Not a technological wall, not a scientific limitation, but something far more complex. A systems wall. And if you look closely, one company appears to understand exactly where that wall is forming. Siemens Energy. At first glance, the problem does not seem obvious. Electrolyzers are improving. Costs are coming down slowly. Renewable energy capacity continues to expand. The narrative suggests that scale will solve everything. Build more wind farms, install more solar, deploy more electrolyzers, and eventually hydrogen becomes cheap and abundant. But this assumption hides a critical flaw. Hydrogen is not a single technology problem. It is a system integration problem. And systems do not fail at the most visible component. They fail at the weakest connection between components. If you follow a green hydrogen project from concept to execution, the complexity becomes clear. You need renewable power generation, often in remote locations. You need grid connections or dedicated lines. You need water sourcing, treatment, and transport. You need electrolyzers operating at high utilization rates. You need compression, storage, and sometimes liquefaction. You need pipelines, trucks, or shipping infrastructure. And most importantly, you need reliable, bankable demand on the other side. Every one of these elements must align perfectly. If even one fails, the entire project stalls. This is where the wall begins to appear. It is not in the electrolyzer stack itself. It is in everything around it. The balance of plant, the grid connection, the infrastructure, the economics of utilization. And this is precisely where Siemens Energy has positioned itself, not as just a technology provider, but as a systems integrator that understands where projects actually break. Consider the grid first. Most green hydrogen projects depend on renewable electricity, but renewable energy is inherently variable. Solar output fluctuates daily. Wind output changes hourly. Electrolyzers, however, perform best when running continuously. If they operate at low utilization rates, the cost of hydrogen skyrockets. This creates a fundamental tension. Either you oversize renewable capacity and waste energy during peak production, or you accept low utilization and higher costs. Neither option is economically ideal. Siemens Energy has been focusing heavily on grid integration solutions because this is where the first major bottleneck emerges. In many regions, grid infrastructure is already congested. Adding large hydrogen projects only increases the strain. Interconnection queues can take years. Transmission upgrades are expensive and slow. In some cases, the grid itself becomes the limiting factor, not the availability of renewable energy. This is a hidden constraint that does not show up in project announcements, but becomes painfully real during execution. Now consider the balance of plant. Electrolyzers often receive most of the attention, but they are only part of the system. Power electronics, transformers, cooling systems, water purification, compression units, all of these components must work together seamlessly. Failures in any of these areas can reduce efficiency, increase downtime, or inflate costs. Siemens Energy's strength lies in its experience with large-scale industrial systems, where integration matters more than individual components. This gives it an advantage in identifying where complexity turns into risk. Then there is the issue of scale. Many green hydrogen projects are being announced at gigawatt levels. But scaling up is not simply a matter of multiplying smaller systems. At larger scales, new challenges emerge. Thermal management becomes more complex. Electrical systems require different architectures. Infrastructure needs expand exponentially. What works at 10 megawatts does not necessarily work at 1 gigawatt. This is another point where projects can hit a wall, and it is one Siemens Energy has been preparing for by focusing on large-scale system design rather than incremental expansion. But perhaps the most critical bottleneck is not technical at all. It is economic. Green hydrogen is still expensive compared to alternatives like natural gas or even gray hydrogen. For projects to move forward, they need long-term offtake agreements that guarantee demand at a certain price. Without these agreements, financing becomes nearly impossible. Banks do not fund uncertainty. Investors require predictable revenue streams. And this is where many projects quietly stall before reaching final investment decision. Siemens Energy understands this dynamic because it operates at the intersection of technology and finance. It knows that building a technically viable system is not enough. The system must also be economically survivable under real-world conditions. This means designing projects that can maintain reasonable costs even if utilization is lower than expected, or if electricity prices fluctuate, or if policy incentives change. It is a much harder problem than simply improving electrolyzer efficiency. Another layer of complexity comes from infrastructure. Hydrogen is not easy to transport or store. It has low energy density, requires high pressures or low temperatures, and can cause material degradation. Building pipelines, storage facilities, and export terminals adds significant cost and time to projects. In many cases, this infrastructure does not exist yet, meaning it must be built from scratch. This creates a chicken and egg problem. Infrastructure depends on demand, but demand depends on infrastructure. Siemens Energy's strategy reflects an understanding that hydrogen cannot succeed in isolation. It must be integrated into existing energy systems. This includes coupling hydrogen production with industrial clusters, aligning with existing pipelines where possible, and developing hybrid systems that combine electricity, hydrogen, and other energy carriers. By focusing on system-level integration, Siemens Energy is addressing the real barriers to scaling green hydrogen. Now step back and look at the bigger picture. The wall that green hydrogen is hitting is not a single obstacle. It is the accumulation of multiple constraints: grid limitations, system integration challenges, economic uncertainty, infrastructure gaps, and scaling complexities. Each of these factors interacts with the others, creating a network of dependencies that is difficult to manage. This is why so many projects look promising on paper, but struggle in reality. And this is also why companies like Siemens Energy are becoming increasingly important. They are not just building components. They are attempting to design entire systems that can survive under real-world conditions. Systems that can handle variability, integrate multiple technologies, and remain economically viable even when assumptions do not hold. The real question is not whether green hydrogen works in theory, it does. The question is whether it works as a system under stress. What happens when renewable output drops? What happens when electricity prices spike? What happens when utilization falls below expectations? What happens when infrastructure delays push timelines back by years? These are the conditions that determine whether a project succeeds or fails. And this is where the industry is now being tested. The early phase of green hydrogen was driven by optimism and announcements. The next phase will be defined by execution. Projects will either move forward and prove their viability, or they will stall and reveal the limits of the current approach. The wall is not a permanent barrier, but it is a critical checkpoint. It forces the industry to confront the realities of building complex energy systems at scale. If Siemens Energy is right, the solution is not to focus on a single breakthrough technology. It is to improve how entire systems are designed, integrated, and operated. This means better grid management, smarter system architecture, more flexible operations, and stronger alignment between production and demand. It also means acknowledging that green hydrogen is not a one-size-fits-all solution. Different regions will require different approaches based on their resources, infrastructure, and industrial needs. Looking ahead to 2030 and beyond, the trajectory of green hydrogen will depend on how effectively these system-level challenges are addressed. If the industry can move past the current bottlenecks, hydrogen could become a foundational part of the global energy system. If not, it risks remaining a niche solution, limited to specific applications where it is already economically viable. This is why the current moment is so important. The wall is not just an obstacle, it is a signal. A signal that the easy phase of green hydrogen is over and the hard phase has begun. The phase where real engineering, real integration, and real economics determine what happens next. And for developers, investors, and consultants trying to navigate this complexity, understanding where these bottlenecks exist is critical. Because the winners in this space will not be the companies with the most announcements. They will be the ones that can design systems that actually work under pressure. If you want to go deeper into how these systems are built, where projects fail before a final investment decision, and how to structure green hydrogen projects that are actually bankable, that is exactly what we break down inside H2 Hub by Renee Energy. It is designed for developers, consultants, and investors who want to move beyond the headlines and understand how to execute real projects in a system that is far more complex than it appears. Because in the end, green hydrogen is not just about producing a molecule, it is about building an entire system around that molecule. And right now, that system is being tested in ways that will define the future of the energy transition.